Yeah.
Welcome back for another second talk on Kline algebraic topology.
Great. So in this talk, I'm going to show you some examples, a couple of examples of exactly how that Kline model work could get used. And then I'm going to switch into more traditional technology and blackboard the rest of the talk, because there's a lot of, I think, some interesting theoretical stuff there, which I prefer doing with chalk and not on slides. OK, so here's what we had. We had built this parametrizing object, this geometric object, the Kline model, which parameterized these high variance, high density patches. And we had even built an explanatory Platonic model, if you like, for it. And so I want to talk about sort of two different directions in which one could use this idea. Now, we talked a bit last time about sort of compression, thinking about how humans want to do compression. And information about density, what happens frequently, is of fundamental importance in building such algorithms. So this is just a simple statement here that can be applied to develop compression schemes. So it turns out that even before we started to look at this, groups in Texas and at Stanford had worked on modifying or building new compression schemes that took into account the fact that the primary circle that we wrote down, the ones which had the linear gradients, were heavy density in there. So they called those schemes wedgelets. Okay, for whatever reason, they call them wedgelet compression schemes. And the work that they did on them, they started to compare themselves with JPEG, ultimately. Now, let me just be clear on what comparison with JPEG here means, because for most compression schemes, there's at least two phases of the work. The one is, oh, you have a clever idea that says, something like this ought to work. And then you do that, and then after you've done that, you then do a million engineering hacks and optimizations so as to get it to really work. Okay? And so there's JPEG, which has been optimized beautifully, and which itself has an underlying idea, but the optimizations are of fundamental importance. So what I would want to do is I would want to say there's sort of a pre-hack JPEG, and there's a post-hack JPEG. Right? And so what they did is they compared themselves. They said, look, we're going to take these wedgelets that we've built. We believe that that's a clever idea. And so we're going to try to compare ourselves with pre-hack JPEG. Right? You don't want to, because otherwise you have to go down the road of doing all the optimizations, which is an enormous amount of work. And and it's an unfair comparison otherwise. And so what they found was indeed that the wedgelets outperformed JPEG in this pre-hacked form. Now you might say, so why didn't they then push ahead and do all the optimizations? And the reason is that people are really kind of happy with JPEG. And unless you produce a huge improvement, like multiples, factored by a multiple, it's not really going to be worth your while. But it is interesting, nevertheless, to see that what one can do in this way. So anyway, they found that it performed better than JPEG. So now one can do the same thing. One can build what we call the Klinelet compression scheme based on this Klein-Bottle's worth of Klein-Bottle kind of dictionary of frequently occurring patches, as opposed to just the primary circle. And in fact, you find, as you would expect, that you perform better, particularly in images where there are lines in here. So I think if you look at some of these, you can see the detail here on the Klinelet. You can see this line here is being captured much more effectively than it is over here in the wedgelet, where there are lots of boxes. And there are sort of quantitative ways of measuring. And so we compared the Klinelets to the wedgelets and found that, in fact, it does better. Here's a similar situation. As you can see, lots of lines in this picture to sort of illustrate or kind of make as evident as possible the level of improvement that you get. Again, though, the improvement is not enough that one is willing to try to go and do all the engineering stuff that you'd need to do. What is interesting, though, is I think it does suggest the possibility, and as I mentioned at the end of the last talk, that for movies and videos, there might be much more bang for the buck in this. And so, I think that's a very interesting direction to pursue. Okay. Now, there's a second kind of problem in trying to study images, which is in trying to recognize and distinguish between various different kinds of textures. So that's sort of a different class of problems from the ones that we've thought. You kind of think of them as kind of solid regions, and there's a line separating the two, or there's a boundary, that kind of thing. But suppose instead it's kind of all messed up in the way that it is in a texture. Can you do something about texture recognition using the fact that you understand the high density, high variance, high contrast patches? So it turns out that you can adopt the following strategy. You can say, look, let me take all the high contrast patches that occur in a given texture patch. Each one of those is some high contrast patch. I can find the closest point on the Kline bottle to that patch. And so what I can get then is a bunch of points, which can then think of as a probability distribution, if I smooth it out a little bit, a bunch of points on the Kline bottle. And so what Jose Perea did, he's a student at Stanford, observed that these distributions that you now get, so each texture patch corresponds to a distribution, probability distribution function on the Kline bottle, can be analyzed because the Kline bottle has such very nice geometry to it. You can do Fourier analysis on it very, very easily, right? It sits as it's covered by the torus, for example, and you just kind of take the invariant part of the involution. So it has a Fourier analysis, and so what he was able to do is to do the following kind of pipeline. Take the textures, create distributions on the Kline bottle, compute their Fourier coefficients, and these kind of give coordinates that represent different texture patches. And it turns out that after he worked with it for a while, he found that the method that he built was comparable to state-of-the-art on certain benchmark data sets. Okay? But, of course, the way that he's built it now says that he has the advantage that the effect of transformations of the image can be analyzed very easily. So, for example, suppose that you rotate the image. Well, what happens here is you'll change the coordinates in a very predictable way. And so it's very encouraging that, on the one hand, you're performing as well as methods that are based on what I would call sort of finite dictionaries, that is a finite list of patches, okay? And whereas we've got our infinite Kline bottles worth of patches as our dictionary, we're getting the same performance as the state-of-the-art, but this additional property that you can understand the behavior of transformations. Right, so you have a bunch of points on the Kline bottle. You get that by doing the following. You take the patch, you take 3x3 patches within that patch. For each one that's high contrast, you find the closest point in the Kline bottle. Okay, so now it's a bunch of points. You can smooth them out with little bump functions. Yeah. Okay. Okay. So yeah, anyway, the kind of picture here, there's a texture on your upper left, kind of straw, and then there is the corresponding probability density function on a rectangular Kline bottle, and he's pictured some of the Fourier coefficients in the upper left there. Okay, so those are a couple of examples of how one could use the finding here about the Kline bottle to get some value out of them. What I want to do now is I want to move away from this, and I want to start talking about a little bit more theoretical stuff. Okay. So one observation that comes out of what we just did is saying the importance of diagrams in extending techniques of topology, right? So this persistence is the creation of a diagram. Okay? And what we've then done is we've said that actually the corresponding diagrams of vector spaces have a simple classification. It's great. And that actually then allows you to extend topology to point clouds, for example. So what I want to argue in this is that, you know, many different diagrams are relevant. So let's talk about an interesting question here. Suppose that I have a very large data set. Maybe it looks like this. Okay. Again, you know, it's a loop, right? Now, maybe it's so large, or I have very limited computing power or whatever. I don't want to have to compute the homology of the whole Vietoris Rips for this thing. But maybe I sample from it, fix a threshold parameter for the Vietoris Rips, and make a computation. So suppose that we have an experiment here. So this is a large data set. And so now I'm going to perform the following. I'm going to say A, you know, sample from it. And then construct V, you know, so S are the samples. And say R for some fixed R. And then C, compute homology. So that's an experiment I'm doing. Okay? And maybe I say that I actually you know, find a lot of times that I do this calculation and it reports back that there's a Betty 1. So suppose it frequently reports back Betty 1. Okay. Excuse me? No, R is fixed. Okay, at the moment, I'm not varying anything at the moment. I will here in a minute vary the S. Unfortunately, I have to hold the R fixed, and we'll come back to that in a bit. Okay. But, well, that is to say, yes, sorry, I have to take multiple samples. You're right. So I take a bunch of samples and compute the homology for them, and often I will get Betty 1 being greater than 0. That's right. So, okay. But let me point out that that could be an explanation for two different kinds of phenomena. One would be this one, and the picture would be that each sample somehow manages to make its way around the circle. But it could also be the case that it would be a more Swiss cheese-like thing where one sample is doing this one and one sample is doing that one and so forth. So the fact that I'm able to report back a homology, you know, it doesn't tell me the difference between these things. So what I want to do here is I want to let's sort of think about how we might distinguish between those two. So suppose that my samples are now S0, S1, S2. Okay, so those are my samples. But now, of course, what I can do is I can actually build the union like that. And both S0 and S1 will include in the union of S0 and S1. And so forth. So now I have a diagram, and I would call this a zigzag diagram. This is a because the arrows are alternating. I have an S0 going from here and an S1 coming from here. But notice that what I could do is I could apply HK, H1 say, and get a zigzag diagram. of vector spaces. Like that. Okay. Now let's think a little bit about what would happen if I were in this regime, if I was constantly computing the same thing. Then what I would have is I would have these vector spaces. This one would go to something in here which came from here, which goes non-trivially here, and which comes from here. In other words, it's like I would have a long kind of sequence or something in the inverse limit of this diagram, something along those lines. Okay? On the other hand, if I had this one, at v0 I'm computing that loop, at v1 I'm computing this loop, they're not going to match up. I'm not going to have kind of long, consistent sequences of elements. Now, what I just said, though, is that's a very fuzzy notion, right? What do I mean by these long sequences of consistent elements? I could make it precise, but fortunately, someone has already made it precise for us. And this came out of the theory of quiver representations. So it turns out that Gabriel had already classified all the possible diagrams for of zigzag type. In fact, what he did, he said the following. So, a quiver is a directed graph. Okay. A quiver representation is just an assignment of a vector space to every node in the graph and a matrix to every arrow. So, or a linear transformation. So a representation is an assignment of vector spaces to nodes. And linear transformations to edges. Okay. And so you could talk about the representation theory of quivers. What are, can you classify up to isomorphism the representations of quivers? And in fact, what we did up here, with ordinary persistence, was doing it for the case of a graph where you have starting point and the edges are just going. Let me say, ordinary persistence is this one. Okay. So, all right, but so it's a rich theory, representations of quivers. Let me give you a simple example that points out, though, one thing that shows that the intuition coming from here is inadequate. See, think about a graph with a single loop in it, like this. What are the representations of that quiver? That's a single vector space equipped with a self-map. And two representations are isomorphic if and only if the two matrices are conjugate. Now, what that means is, you see, that the classification here is essentially different from here, because this classification is just kind of some ranks and things going on. It's a discrete classification, and it's independent of the field involved, right? The target for the classification. Here, though, this is Jordan normal form, conjugation of matrices. And so the elements of the field play a critical role. So this classification here is not, I'll just call this a non-finite classification. Okay. And we don't like that, or we prefer not to deal with that. We don't think, for example, that anything that we do here should depend so much on the field of coefficients. Because, when you do homology with rational coefficients or with real coefficients, it contains essentially the same information. So what Gabriel did was he identified all quivers for which the classification is finite. Okay? So Gabriel identified. And the answer turns out it's actually a rare thing. This is the much more typical phenomenon. But it turns out here that it's precisely all those quivers, which are directed graphs, whose underlying undirected graph is a Dynkin diagram. If you're familiar with that, the Dynkin diagrams are the things that come out of the classification of Lie groups and of representations of Lie groups. So this occurs exactly when the underlying undirected graph is Dynkin. In particular, what that says is, now, look, suppose that I have a little more foresight here. Okay, so in particular, if we have this one, the underlying directed graph here is exactly the same as the underlying directed graph for the ordinary persistence, and it's got a discrete classification. In fact, the classification is identical to the one for the ordinary persistence. So let's talk about by a cyclic module. So let me just write cyclic quiver rep. What I mean by a cyclic quiver rep here is one which is either 0 or a copy of the field. There's nothing more than rank 1. And furthermore, all the occurrences of K are adjacent. So for example, this would be 1. And all the maps should be the identity. That's a typical cyclic quiver. And it turns out that or quiver representation of this one. And so it turns out that every diagram of this shape of vector spaces can be written down as a uniquely as a direct sum of cyclic things. Each one of these cyclic things has a bar attached to it, so there's a barcode classification here as well. And so what that means is, you see that now we can make sense of what it means to have these long consistent sequences. It's, are there long bars present in the decomposition? So the existence of long sequences is the same thing as saying there exists long bars in this decomposition. So that's a way of approaching this whole sampling question and trying to distinguish between the two possibilities that I mentioned up here, this one and this one. Okay, now it turns out though that maybe that once you realize this, there are many, maybe even more interesting applications of that. So suppose, for example, that you have some time varying data. So suppose we have data with timestamp. One interesting thing that I could try to do is I could say, look, let me break up my data. So X is my data set. So, and I'm going to write X of S and T is the data points whose timestamp is between. So I'm taking parts of the data set, and I'm going to try to understand how the data varies over time, how the structure of the data varies over time. And so what I could now do is, you see, build a zigzag like this. Maybe I'll do something like this. Well, what should we do? Yeah. I'm going to just and so forth. So I can build a zigzag diagram based on the time coordinate instead, or any coordinate that I like. And what that means is I'll now effectively be studying. You see, with homology here, persistent homology, we studied, if you like, the homology of sub-level sets, right, or of things where some threshold parameter was less than something. Now this gives us the additional capability of trying to study it for just kind of level sets, for things which are a piece bounded below and above. And so it turns out that this is quite a powerful thing to do, even in this kind of context. Or if you think about the situation we were in with that Kline bottle example, remember there I think I mentioned it, we had to choose a threshold density, a density threshold. So with the Kline bottle example. Chose a density threshold. Can we let that vary and divide into zigzags? So in any case, these zigzag diagrams allow you to understand the way that the homology changes within these more like level set situations. Okay. But now comes what I regard as kind of the biggest thing here. See, over here, even doing this zigzag, you notice I had to take the step of fixing R because I was going to try to vary something else, namely I was going to try to vary the samples. Same applies over here. If I'm going to allow this density threshold to vary, and I just want a single parameter varying, I have to fix something else. I'll have to fix the scale parameter in my original complexes that I built, which is awkward. In fact, in general, when studying any data set, density is almost always of interest. Okay. So what I would want to do is I would want to have a threshold parameter delta. So delta is a threshold parameter for density. But of course, I also want to vary my scale parameter. I don't want to fix that. That's sort of the whole reason we got started with this in the first place, because we knew we didn't want to have to choose that. So I want to vary, so let's let R also the scale parameter. Suppose I want those to vary simultaneously. Can I vary them simultaneously? That's the question. Okay. So what would that mean? There's sort of a good formal answer to that question. Of course you can, just do it. So we'll write down what it means. So, by persistence, by d-dimensional vector space, say, what I mean is a bunch of v S1, S2 through SD, like this. So the vector spaces are now parameterized by d different parameters. And I have maps from the one to the next one if all of these are less than or equal to the ones in the new one. So what I have now is if d equals 2, instead of having a sort of a long line of vector spaces, I have a rectangular grid. And so if I do the following now, if I'll say, for example, let's say we have a data set, so X is a metric space, with some density estimator or some proxy for density. So I have that density function on there, and I have the scale. I can then talk about like this. You know, the simplices are points x naught to xk. Is less than or equal to r. And then furthermore, that delta is actually, and this I'm going to, typically one wants to do, is greater than delta. I'm turning the arrows around because typically one wants the large ones to enter in first. Okay. So there's an obvious now two-parameter family of simplicial complexes, and I can apply homology to it to get one of these two-variable persistence vector spaces. So the question is, are there barcodes? Is there something like a bunch of rectangles instead of a bunch of lines? So let me tell you what the answer to that is. So it turns out that just like for ordinary persistence vector spaces where they were assigned to graded modules over k of t, so these d-dimensional persistence. This is an equivalence of categories to a d-multigraded modules over so in other words, these are things whose grade, which has d different gradings to it. So think of each variable as having a degree, say ti is 0, 0, and then a 1 in the ith slot. Okay. Now, one of the first things that you learn when you start doing commutative algebra is that the classification of modules over polynomial rings in more than one variable is a whole different beast from a single variable. Okay, there are sort of moduli spaces of such things as opposed to the classification being discrete. So this classification of such module is really intractable. In fact, you find that the classification depends in an essential way on the structure of this ground field K, which is another principle that we don't want to, that we'd really like things to be independent of that. Okay. Okay. All right, so that at least tells us we've got kind of a difficult problem here. Now, we have things we can do. We have some invariants, which would be, like the rank invariant, which would be called the function rank of, say, VST to S prime T prime is a discrete invariant. But it's unsatisfactory here. I mean, we don't know what to do with it. We knew when we see a persistence barcode and we see a long bar, we know that's a feature. That's something that we're interested in. How do we make sense of long bars and so on here? I don't have a complete answer to that. But what I'm going to tell you about now is some work on the single variable side, recasting that in certain ways, which might get us to this, to something, to trying to understand this situation. Okay, so now, so I want to just write bad news. So back to 1D for the moment. Okay, so here are some interesting facts about 1D persistence. So, So let me remind you. So there exists a metric called the Gromov-Hausdorff metric, for distance, on the set of all compact metric spaces. Okay. And it's defined, it's one of these things that's very easy to define if you don't concern yourself with how it has to be, how to compute it. The way it's defined is this. You take two metric spaces, x and y. Okay? And what you do is you pass over all possible isometric embeddings into some third space. So over all isometric embeddings, I sub x into z and I sub y from y into z. Okay? Over all such, and now you're going to hope that the images are close, so there's a notion of Hausdorff distance. So compute Hausdorff distance of the image of Ix of x from So Hausdorff distance is something when you have two sets. What you can do is you can compute the distance from every point in the one set to the other one. And now you take, is it a max or a min? There are a lot of quantifiers here, but basically if the one can get overlaid perfectly onto the other one, the distance is 0. If it's sort of close to being overlaid, then the distance is small. So that's a Hausdorff distance of these sets. And the Gromov-Hausdorff distance is the infimum over all possible embeddings like this of that Hausdorff distance. So is the infimum of the Hausdorff distance over all of these. Over all embeddings into all possible z's. I'm sorry, is it what?
Is the infimum attained?
I don't know. I doubt that it would be. I doubt that it would be obtained, necessarily attained. I don't know. Maybe even a finite case if you fix the number of points. It's a good question. In any case, here's something which makes perfectly good sense and which obviously on the face of it is hopeless to compute, at least directly, if we're going to try to actually follow the definitions. And in fact, it's not just that it looks hard. Basically people don't have any good reasonable methods that work for even some small finite metric spaces. Okay. All right, so that's an interesting fact up there. That's the distance on the set of all metric spaces. So let's write M, all finite metric spaces. Turns out there's also a notion of distance on barcodes. Okay? So there's also exists distance. There exist distances on barcodes. And the way those work is, these are kind of like, so they're similar to edit distances. Okay. What that means is, two barcodes, you have a collection of intervals. You allow yourself moves, which are to sort of change the endpoints of one of the intervals, or even delete one of the intervals. But for each such move, you pay a penalty, and the penalty is something like how far did you move the endpoints, how long was the interval you removed. Okay. And so there's a bottleneck distance, as it's called, which is one of these. So which is obtained by taking an infimum over all possible edit sequences of the penalty. So that's, now, so I've written down something else which also includes an infimum, and so you would be right to worry about, well, so is this tractable? But it turns out that this is something that computer scientists understand very well. These distances can be computed very fast and very easily. Okay? So a bottleneck distance can be computed easily. And then the third fact now, which is a theorem of Mimoli and Udo, is that now if I take my m here, and with its distance function d Gromov-Hausdorff, for each finite metric space, I can now assign to it its k-dimensional barcode. So this is the set of barcodes. With here, this is distance bottleneck. So this is a map, is a function from the set of all metric spaces, all finite metric spaces, to the set of all barcodes. And the theorem that they prove is that beta k so it's got sort of a continuity property to it. Now, I can't emphasize enough how well, let me explain why this is important. Even it's kind of independent of this. Suppose that, so we've been talking about using topology and homology to understand an individual data set. But something else that might happen is we might have what would be thought of as an unstructured database, a database that consists of objects which themselves have a notion of distance on them. Think of chemical compounds, for example, where you might have all the atoms in the compound and the distances between them, or perhaps the distances across computed by bond lengths. So what this says is, if I have a database whose objects themselves are finite metric spaces, all of a sudden now I have functions on them, where I have these to barcode space. And so the barcodes so if my database objects have a metric, Betty K can be used as a generalized index or indexer. Yeah. It's whatever dimension barcode you take. So you've actually got a bunch of them, right? So if I take Betty naught, Betty 1, Betty 2, this is Betty K. A second fact, which is sort of, this is kind of theoretical interest, is the fact that now I have cheap to compute lower bounds for the Gromov-Hausdorff distance. So we obtain lower bounds for DGH, which are easy to compute. Okay, so what this is doing, think of this as producing a bit more structure to the set of barcodes. We've thought of it as just a family of sets. Now we're thinking of it as it's a metric space in its own right, and it's clear what it means for one to be close to another and one to be far. Okay. Okay. But now I want to move to another description or another kind of organizing principle or organizing methodology for barcodes. Second, rather than putting a notion of distance on it, suppose I tried to make coordinates on it. Okay? Let's think about that. Can we make coordinates? Okay, well, let's start away. Let's take something simple first of all. Let's just take the set of barcodes with n bars. Okay? So let's let Bn What does that mean I have? That means I have n intervals. It means I have a bunch of pairs of points, x1, y1, x2, y2, and so forth. So I actually have 2n coordinates. So I can consider the birth points, x1 through xn, and the death points, so those are kind of coordinates. But they're not really, because remember, the set we want to consider is the set of sets of intervals. It's not ordered sets of intervals. Right? So we really want unordered things. Unordered lists of intervals. Okay, so let me say, this, of course, would give me a variety as an affine variety of dimension 2n, right? x1 through xn, y1 through yn. Okay. Now I'm going to be considering only those functions which don't depend on the ordering that I placed the intervals on. That is to say, this should now, these are the points variety associated to the ring fixed under sigma n. The invariant subring here on the action of n acting on a bunch of x's and a bunch of y's. Now, if we were acting only on the x's, we would know what this looks like. This would look like the polynomial ring on the elementary symmetric functions, sigma 1 through sigma n. So let me just write R sigma I are the elementary symmetric functions. Unfortunately, when you have the two variables, two sets of variables like this, it's no longer just a polynomial ring. The ring actually has relations and syzygies and things. Okay? But nevertheless, it exists as a ring. So let me just write down R of x1 not a polynomial itself. But now what I want to do is I want to assemble these rings in a certain way. So let me take you by analogy. How are we doing? Okay. So there's an inverse system. If we think of just, we can think of I can actually build an inverse system of rings like this corresponding to the direct system, which takes an n tuple and adds 0 to it to get an n plus 1 tuple. And so I get an inverse limit of rings here and of graded rings, inverse limit of graded rings. And that inverse limit is, of course, R of sigma 1 with no bound on everything happening. It's important that you take the inverse limit in the graded context. Okay. So what happens with this one? So with this one, so there's a corresponding inverse system. And it turns out that although the individual constituents here are not polynomial, the inverse system is. So the inverse limit in the category of graded rings is polynomial. Okay. All right, so that's good, and you can actually tell what they are. These are so-called rings with multi-symmetric polynomials. It's an area within algebra which I would have thought would have been done in the 19th century, but in fact, some of the results are still coming out on this. It's pretty, or have been in the last 10 or 15 years. All right, so that looks reasonable, like something that we could be interested in. I claim we want one more feature, though. We would like to have it be the case that we want to consider only functions which respect the following operation. So which respect the operation of dropping an interval of length 0. Right, because for us, something that sort of is born and then dies at the same time, that's non-existent. We don't want to include it. Okay? And that actually changes the algebra here. The subring of this inverse limit, which respects that relationship, is still polynomial. Is polynomial. With n generators in dimension n. Okay. So it's a rather easy to understand ring. The first linear function is the sum of the lengths, or the sum of the differences yi minus xi. Okay. The next one has in it the sum of the squares of those lengths, but also something that looks like summation like that. So it will also, these functions will also include information not just about the lengths of the intervals, but about the placement of them. Okay. Okay. Now, so there are some benefits to this point of view. So this is saying we're not going to think of it as a metric space, or we're in addition to thinking of it as a metric space, we're going to think of it as some kind of infinite algebraic variety. So, benefits. Okay. First benefit sounds kind of funny, but it's true. when you start engaging and talking to people sort of outside of topology, specifically people who are in an area called machine learning, where people are trying to study data with a lot of linear algebraic and nonlinear methods, they don't like barcodes. When you tell them, oh, I can give you a barcode, that's not a good thing. Okay? On the other hand, if you can give them numbers attached to things, that's a very good thing. So the benefit is A, we can automatically produce numbers instead of barcodes. In fact, we can produce lots of numbers. So if we now think of one of those unstructured databases that I described before, where I said, look, we can assign barcodes to them and use those as an index. Now we can do more. We can assign coordinates to them and actually put them in tabular form and put them in a spreadsheet or something in a principled way. Okay, so I can build tabular databases. From unstructured. But there's a second point here, which is, let's go back to that question about the multidimensional persistence, where I mentioned that the moduli spaces of these modules are very, very bad. They're very complicated. Is it possible that the functions we've built here extend naturally to the multi-D setting? In other words, we don't try to put a square peg in a round hole and build barcodes out of multidimensional persistence, but maybe some of the functions which we actually know how to interpret quite well, maybe those extend so we can study the functions on these complicated moduli spaces instead of the moduli spaces themselves. Just an indication, and then I will stop, of and this is just sort of an indication. This is not that this is a practical procedure, what I'm going to tell you right now, but I think it's a very interesting result due to my student Pavin. See, one thing that you could do, let's consider ordinary 1D persistence. So for a given barcode, I could lose some information and keep track just of the set of birth points and the set of death points. So, so the barcode. So S death and S birth. It loses information because you don't know a given birth point, which death point is it associated to. So you definitely lose information. It turns out, though, that this construction, we can make very good sense of the death points and the birth points in the multidimensional setting, it turns out. I can talk about that afterwards if anyone wants to hear. So this is something we've lost information, but it's something which generalizes. Now, what Pavin proved was the following. He said, look, let's do this. Let's start out, so M is a persistence module. Now, when I have a persistence module over any ring like that, I can build its exterior powers. So I can build lambda k, let me call it lambda t, over k of k, just not hitting it today. Let's see, lambda a k of t. So I can build a bunch of modules like that, of persistence modules. This exterior power is a standard definition. What Pavin proved is that if you take all the birth and death sets for all these exterior powers, you can recover the barcode. Okay? So let's see. So of lambda A. Allows you to get back to the full barcode. In other words, that gives you the matching information between the birth points and the death points. The advantage of that is, you see, it says we have recovered here the barcode, but the constructions that we've done here are things that we could do over the multidimensional polynomial ring. Namely, we can build these birth and death points, and we can compute the exterior powers. So it suggests at least, something in the direction of saying, look, we're going to get something which has deeper information about the multi-persistence module than just its death and birth points, and something which is, in fact, gives complete information for single variable persistence. Okay. So again, this is kind of intractable. There's a lot to do here, but it suggests that the idea of trying to say, let's get at the functions, or let's try to generalize some things from single variable beyond just the existence of barcodes themselves to try to get at some information about this multidimensional stuff. Okay, so I think I'll stop there.